Good day, folks. I am Janine, and in this video, we are going to tackle mathematical induction and how we can use induction to prove that a conjecture is true. Well, first, let us unpack what is mathematical induction. Mathematical induction is a technique of proving a statement, theorem, or formula which is thought to be true for each and every natural number n by generalizing this in form of a principle which we would use to prove any mathematical statement. And this is principle of mathematical induction. Now, let's use induction to prove that a conjecture is true. Let's consider the following expression. This expression is a sum of first and positive even integers, where n can be any natural number. Based on that expression, we come up with the following formula. 2 plus 4 plus 6 up to 2 multiplied by n is equal to n multiplied by n plus 1. Now the question is, how did we come up with this formula? How do we know it's applicable for any natural number n? We cannot check the accuracy of the formula for all terms of the expression one by one, as it would be very time-consuming. And so, in order to check the validity of the formula for each term, we need a domino effect, showing that if the formula is true for one integer, then it will also be true for the next, and so on. Now, in this portion, let's get to know domino effect. Suppose you queue several dominoes one after the other. How would you position each of these dominoes in order to ensure that all of them fall when you hit the first domino? Logically, we know how to achieve our goal. But how do we write it mathematically? The best way to achieve your goal is 1. When the first domino falls, it will hit the second one. And 2. Make sure that each domino will hit the next one, and each domino that is hit will fall. When these two conditions are satisfied, no matter how many dominoes we queue, all of them will always fall. Comparably, in mathematics, to prove the formula true, it has to fulfill two conditions. The first condition is a FAT, which is also called as the base case. The formula will be true if P of 1 is true for n equal to 1. Here, n is equal to 1 represents the first term. But what is P? P is a propositional statement that has a definite value. This value can be true or false. Suppose we have the statement x is hot. Then P of x can be true or false, depending on what x is. When x is fire, P of x is true. And when x is ice, P of x is false. Now we know the first condition to prove a statement true. The second is a conditional property, also called as the inductive step. If we assume that the formula is true for n equals to k, then it will also be true for n equals to k plus 1, thus creating the domino effect which we spoken about earlier. It could also be thought of as P of k implies the truth of P of k plus 1. This assumption that we make, the assumption of the formula is true for n equals to k, is called as inductive hypothesis. To understand this better, we have an example. 2 plus 4 plus 6 up to 2n is equal to n multiplied by n plus 1. Let this be P of n. Now, we will check the first condition. When n is 1, P of 1 has to be true. Let's look at the left-hand side first. When n is 1, we will just consider the first term. So, P of 1 for the left-hand side is 2. Now, we move on to the right-hand side. P of 1 for the right hand side will be 1 multiplied by 1 plus 1. This is 1 times 2, which is equals 2. Therefore, P of 1 for the right hand side is also equals to 2. The first condition is done. Now for the second one. For the second condition, we first assume that n is equals to k. So what will b of k be equal to? P of k is 2 plus 4 plus 6 to 2k is equals to k multiplied by k plus 1. Based on that assumption, we have to prove that the statement is also true for the k plus 1 case. The left-hand side of p of k plus 1 is 2 plus 4 plus 6 up to 2k plus 2 multiplied by k plus 1. How do we simplify this? Well, look at this part. We have already seen that this is equal to k multiplied by k plus 1. So, we can replace this part with k times k plus 1. We can see that the part k plus 1 is common to both the terms. Hence, this can be simplified to k plus 1 times k plus 2. Now, to calculate the right-hand side, we replace the k with k plus 1 in this expression. Hence, we get the right-hand side of p of k plus 1 as k plus 1 multiplied by k plus 1 plus 1, and that gives us k plus 1 times k plus 2. Therefore, we can say that the left-hand side of p of k plus 1 is equal to its right-hand side. This means p of k plus 1 is true, and the inductive proof is now complete. Consequently, by the principle of the mathematical induction, we can say that p of n is true for all natural numbers n.